Hello and welcome to our explanation of the examples of section 1.4, continuity and one-sided limits. So I want to first discuss continuity with you, and continuity is basically what it sounds like. It is a function is continuous, and I had a professor once describe to me that a continuous function is any function that when I draw, I never pick up my pencil. It doesn't matter if it's got sharp points or anything like that. It just can't have any gaps in it or holes or anything like that. So that's what we're talking about when we're talking about a function being continuous. So first thing we look at is this graph right here, 1 over x, and I graph the function so we could get a picture of it. You could see that if I put in 0 for x, the graph doesn't exist there, so this is a non-removable discontinuity. And it's not removable because there's no way I can change the function so that it would be continuous at 0. The second function down here has a removable discontinuity, because if you look closely right here, there is a gap missing at 1, and that's what I left this table up here for you to see. This is the table of that graph. There's a gap happening at positive 1. So this is a removable discontinuity because I could factor this and say x plus 1, x minus 1, and then over x minus 1, and I could cross out the x minus 1s, and so x plus 1 is the approximate graph for this, but in this graph itself it is discontinuous at 1 because there is a hole in the graph, and so this is a removable. This is removable, and we like to use the word hole as what it is, as a removable graph. Moving on to the next one down here, this function is a step function, as you can see, but you can see that at 0, it looks like if I put 0 into the first function, I get 1. If I put 0 into the second function, I also get 1. So where 1 stops, the other one picks up. Even though these graphs aren't necessarily a nice smooth curve, it might be a sharp point there, this is a continuous function because where 1 stops, the other one picks up directly. So this is a continuous function. Sine function is also a continuous function because this is what we usually think of when we think of continuous functions. It's nice and smooth and moves along and stuff like that. And the AP people love to ask this question and ask if it's continuous using a step function. So you just check it by plugging in the values for x into both of them. And if they end up being the same value, it's continuous. So then moving on, this time we're asked to find a limit, and the whole reason that we do the continuity discussion is the fact that in a limit, if a function is not continuous everywhere, for example this function right here, we can do a limit from one direction, and we can basically find out what's happening, and that would be our limit of our function. So we're asked to find the limit as x approaches -2 from the right hand side. We use this little plus to represent the right hand side, and so I'm looking at my x values as I move across, and basically what I'm trying to do is find out what my y values are approaching as I approach that -2 from the right hand side. And so for my function f of x, for that square root of x minus 2, or square root of 4 minus x squared, I get 0, because you can see my y values are falling ever closer to 0. Now, if I ask for the limit as we approach -2 from the left-hand side, from over here, there's no function, so it doesn't exist. So that's why we denote right hand or left hand, is because sometimes the function doesn't exist where we're trying to approach from. So then, if you haven't seen this greatest integer function, it looks something like this. It's a nice little step function. You can graph it on your graphing calculator. I left this up here. This is my table. I found the int, that's intx, which is greatest integer function, under math, and then you arrow over to number, and it's like the 5th one down or something like that. And it's int, and then you'll get this nice little step function. Well, you can see that in the step function, if I want to approach what's happening when I approach 0 from the left side, the little negative of f of x, of my step function, then you can see from the left-hand side, as my x's are getting closer to 0, I'm down here at -1. If I look at my limit as x approaches 0 from the right-hand side of f of x, of the greatest integer function, you can see that I'm at 0. And so basically, the blue one, I was approaching 0, and the red one, I was down here approaching -1. So the question is, if we approach two different values, does the limit exist? Well, the limit of f of f of x as x approaches 0 does not exist, because from either side, they approach two different values. From the left-hand side, there's a value. From the right-hand side, there's a value. But overall, it doesn't exist. Okay? So then we have functions where they want us to describe the intervals where things are continuous. Well, I graphed the tangent function, and I showed you the window down here to show you what the tangent function, what window I was using. This is just 2 pi, negative 2 pi. This is positive 2 pi. This was 2 pi, negative 2 pi. This was positive 2 pi. And then this value is pi over 6. And so those are the values that I plugged in. And so you can see that this is negative pi over 2. This one is pi over 2. Basically what I'm writing is the vertical asymptotes. And so every pi over 2, 1 pi over, is where the thing is continuous. So if I wanted to write an interval, I would say pi over 2 plus pi n. And basically that's just saying that the distance between the two vertical lines is pi. This is a distance of pi, and we're just saying how many pi's am I moved over would tell me where I was at. So then we saw earlier that the sine function, we saw this function that goes up and down and oscillates, it doesn't exist, and partly because if I just treated 1 over x as if I plugged in 0 for that, I get it does not exist there. So there is no value for 1 over x in this case. And so what ends up happening is I can say, well, my function is not continuous. Even though I put in this point, it's not continuous function because I'm oscillating back and forth. Then my interval that it is continuous on is negative infinity to 0 and 0 to positive infinity. Even though that point's filled in, because at that point our function is a vertical asymptote, as we saw earlier in our graph. Our graph goes to infinity or negative infinity. So there can't fill in a value there. Now this guy over here is actually a couple functions graphed. This is x sine of x is the one that's the curvy one that's going up and down. These guys are the absolute value function, and the reason I did that is because I can use the squeeze theorem and say the negative absolute value of x is less than x sine of x, because this is a damped harmonic motion, which is less than or equal to the absolute value of x. And since these guys are less than or equal to, and this guy is squeezed in between, that when I plug in 0 into this function, well, I would basically use my two absolute value functions, the upper absolute value and the lower absolute value, to squeeze in. And those, since this function is following those absolute value functions as it squeezes in, we can use those as our limit. And so our limit of this function is basically, or our interval where it's continuous, is it's continuous everywhere. And we're using the squeeze theorem. We're using the squeeze theorem to help us determine this, that that value, there is a value of 0 in there that this thing gets really close to. It becomes 0 and then keeps going. And so we're using those absolute values in the squeeze theorem to help us do that. So then we have the intermediate value theorem, and you can go ahead and read this. And the intermediate value theorem basically says that if you have a function that is continuous, then a continuous function, then there is some point in between the two endpoints, or the 2 points you're looking at, that this function must have crossed. And so my example here is that a girl's 5 feet tall on her 13th birthday, 5'7" on her 14th birthday. So somewhere between her 13th and 14th birthday, she might have been h, which could have been 5 feet 5 inches. And so that's really what we're talking about. So somewhere in between 5 feet and 5'7", she had to be 5 feet 5. That's really all. That's all this is talking about. Now this is an existence theorem. It doesn't prove that it proves that there is a time when it is, but it doesn't show exactly when it is. It'll just prove that there possibly exists a time when she was 5'5", not that where it is. And that's the other thing. Okay, so the intermediate value theorem only shows us that there is one. It doesn't show us exactly where it is. We have to do some other work to show exactly where it is. So this is a use of the intermediate value theorem, and the function is f of x. F of x is x cubed plus 2x minus 1. I graph that function, and so we're looking at the interval between 0 and 1. We want to show that there is a 0. Basically, we want to show that this graph is crossing the x-axis. Well, if you don't have access to a graphing calculator, what you can do is say, well, if I do f of 0 into this function, 0 cubed plus 2x minus 1, and you have to first say that this function is continuous, which it is. Polynomials are continuous. And since it's a continuous function, then we could say by plugging in these 0 values for x, I could simplify this and say, okay, well at 0 I'm at -1. And then what ends up happening is if I plug in 1 into the function, I get 1 cubed plus 2 times 1 minus 1, which I believe will end up giving me the value of 2 at 1. You can see it right there. So when I was at 0, I'm down here at -1. When I'm at 1, I'm up here at +2. And so you can see that somewhere in between those guys, between 0 and 1, there must be a 0 of the function. There must be a place where it's crossing the x-axis. So by the intermediate value theorem, that's supposed to be a v, intermediate value theorem, there exists a 0 between 0 and 1 for my x's. So there must be a place where y is equal to 0 between 0 and 1. And so this is what we're talking about. You first have to mention that it's a continuous function. And once it's a continuous function, then you can go ahead and check this, and then you can say by the intermediate value theorem there is a 0 because we just showed it up there. This proves the intermediate value theorem. So that is all our examples for today in this section. So thank you for joining us, and I will talk to you guys soon.